Awesome. Thank you very much. Yeah, and welcome everybody. Thank you for joining my talk on Flawed machine learning, top vulnerabilities in the machine learning lifecycle, and how to avoid them. A little bit about myself. I'm currently engineering director at Ceylon Technologies. This is a open core machine learning deployment and monitoring company. I am the chief scientist at the Institute for Ethical AI, where we develop frameworks to ensure the responsible design, development, and operation of machine learning systems. And I am governing council member at large at the ACM. So today we're going to be covering a very interesting topic, but also very practical. We're going to be using a lot of resources that you will be able to try out yourselves. So you will be able to access all of these tools through this repository. So if you go to ethical ML/FML security on GitHub, you will be able to find the Jupyter notebook that we're going to be using throughout this entire end-to-end showcase. And this is going to cover examples of this flawed machine learning, the link to the slides, and also the examples of the solution that we will cover of basically how to address some of these ML security challenges. Just to set the scene and to see basically what are the challenging that we're trying to talk about, what is the challenge that we're trying to talk about in this session is the question about security in the machine learning lifecycle. And the key consideration here is that there is a lot of resources already available around security for normal software, right? And for general developer operations type contexts. So there's no question about that. There's a lot of resources for that. And what is interesting is that there's not as many resources specifically for security in machine learning. There's a lot of resources on machine learning applied in security, things like automation for prediction of malware or spam detection. But when it comes to actually best practices and topics around security for machine learning itself, it's not as designed. So it's not as fleshed out. So what we're going to be doing today is that we're going to try to define some best practices and also some bad practices when it comes to machine learning itself, and identify some of the more common challenges that appear which introduce vulnerabilities throughout the life cycle of a model. And we're going to be taking the similar approach that is taken in general security of software, which is that it's impossible to make systems completely unhackable. So that's not possible. But what we can do is we can introduce best practices that allows us to mitigate undesired outcomes. And we have to remember that the solutions, even though they will be technical in nature, ultimately they will still rely on humans and process, right? And that's always the case for the topic of security. We're going to be introducing this concept called MLSecOps, which is basically a growing topic within the field of ML and MLOps. So this is the intersection and the extension of DevOps and security with machine learning as first-class citizen. And basically, in more tangible terms, is the intersection of the machine learning infrastructure, developer operation and automation, and the security policies. So this is basically the umbrella term that we're going to be using to showcase all of the topics that we discussed during this talk. And as I mentioned, we're going to be making use of all of the resources that have been made available to us in non-machine learning use cases, right? This is an example of a very popular industry standard for security called the OWASP, the Open Web Application Security Project, which releases an annual report called the OWASP Top 10. These are basically the most common vulnerabilities that appear in general software. And these are things that you may have overheard, things like dependency injection, broken authentication, undesired access to resources. But the key thing is, the only reason why I'm showing you this is because by the end of the talk, we're going to end up with a one-to-one mapping of this OWASP Top 10 for general software into an OWASP specifically for machine learning. So what are the top 10 vulnerabilities that appear in machine learning and how we can address them? That's what we're going to be doing today. And this talk is, of course, about machine learning, but we only have 45 minutes. So we are going to actually skim through a lot of the topics that we normally, or I would normally go into a lot of detail. So one of them is actually the steps that we're going to be carrying out to convert our machine learning model into a fully fledged production microservice that we can consume for predictions. All of this, is going to be a bit hand wavy, but if you're interested, I have done several talks, actually one at the ODSC last year, where we talked about the actual step-by-step best practices of machine learning deployment. So today we're going to be focusing on the security considerations. So we're going to overlook the actual steps to deploy. But if you're interested on the resources, please do check out the resources from the links that we put. But this is what we're going to be doing. We're going to be just taking a machine learning model. We're going to package it. We're going to deploy it. And then we're going to consume it in a production sense. We're going to talk about security in this context, right? So that's what we're going to be doing. And the way that we're going to be doing this is we're going to be using this tool called Seldon Core. This will allow us to actually productionize our models into fully fledged Kubernetes microservices. So again, we're not going to be covering a lot of the details of this, but the key thing is that these are going to be production machine learning services that we're going to be interacting with and that we're going to be dealing with the production security levels of. And what this is going to look like is we can actually have either our machine learning artifacts or our custom Python, Java, or R code that is converted into a fully fledged microservice that exposes a REST, gRPC, and Kafka interface. So let's actually get started with that. So what we're going to be doing is we're going to be taking the hello world of machine learning. This is the iris classifier. As practitioners or even as someone coming into the field, it is quite intuitive. We're going to be taking the iris classification dataset. This is basically the classification that contains specifications of flowers and predicts which of them it is, which class it is. We're going to be using a logistic regression model, and we're going to be using our training data to train that specific model. Now that we have a trained model, we can use that model to perform predictions, right? So that's basically the 101 of machine learning. But now there's the question of, we can now have a model that performs predictions locally. We now want to actually package it and deploy it. The way that we're going to be doing that is we're going to actually, create a directory and save that artifact, right? And the way that you tend to save artifacts in the scikit-learn world is using this library called joblib or pickle, which you basically save the binary version of that file. If we have a look at what's inside of that binary version that we just exported, it's actually quite intuitive, even though, initially you would imagine that it's just, gibberish, but it's actually quite intuitive. So the first, it just saves it into this, bytes array that contains as a first, parameter, the module, the Python module, which in this case is the scikit-learn logistic model module, then the class, which is the class logistic regression, and then the parameters that are passed to initialize that. This is how Python knows what to do whenever it loads a pickle, right? So now that we have this, pickle or this binary of our model saved on a file, we can actually upload this file into a remote location because we somehow need to make sure that to deploy our model, it has to be accessible for it to be deployed, right? So we're going to put it in a Google bucket or S3 bucket or Azure bucket, and then we can deploy it using Seldon, right? And the way that we do this is by interacting with the Kubernetes API. We basically just tell it, hey, my model was uploaded into this path, right? In this case, it's FML artifacts/save. That's our save model, right? We actually apply that, and we can see that now our model is running, right? So that's now our model running as a microservice. And similarly, we can now send a request, right? Similar to that initial prediction that we did locally, right? Where we predicted that input data. We are now doing the same thing, but we're not doing it directly with a REST request, passing the input, which could be like the size of the petals, and then the output is the class that it predicted. So it's exactly the same thing. Right now it's predicting for class number 2. So this is basically the 101 of machine learning. Again, as I said, very hand wavy. If you're interested on the details, you can check the other talks that are linked. But remember that today's talk is about security. It's not about machine learning deployment. But now that we've actually deployed our model and we've touched upon several steps of the machine learning lifecycle. So if we look at the LFAI, the Linux Foundation's AI, sub foundation, what are the sort of different steps of the machine learning lifecycle? So we actually went through data cleaning, the data validation, feature engineering. Then we actually trained our model, if you remember. We didn't really perform validation to ensure that the statistical metrics are as required. But ultimately, let's assume that it got to a point where we're happy with the model, and then we deployed that model, right, and served it, and then consumed that. And in theory, we monitored it, etc., etc. So now, if we take a step back and we ask the question of, if we were to follow this end-to-end machine learning lifecycle from a scale at scale with multiple team members handing over like the models at different stages, what are the areas where there could be security vulnerabilities introduced, right? And that's actually quite simple. The only areas where you can have security vulnerabilities are basically the areas in red, right? So basically, absolutely every single step of the machine learning lifecycle has potential, risks where security vulnerabilities can be introduced, right? At the data ingestion, at the data cleaning, at the feature engineering, at the model training, at the exporting of the model, at the deployment of the model, etc., etc. So you can see now that, especially as the capabilities, the MLOps capabilities scale, there are further considerations when it comes to this question around security. And what we're going to be doing today is we're going to be tackling this from a very pragmatic way. And we're going to be asking the questions of, first of all, what are bad practices in machine learning? Like, what are those things that if we were carrying out, it would not be good, right? Like, this is flawed machine learning. And we're going to be looking at flawed machine learning at different levels. We're going to be looking at flawed machine learning at the step where we load the model artifacts, the step where we provide access to the machine learning model, black box access, white box access, the dependencies of the model runtime, the vulnerabilities within our code, the vulnerabilities within the runtime images, as well as some honorable mentions in terms of infrastructure itself. So let's dive straight into it. The first part being the artifacts themselves. So as practitioners in the machine learning space, we all at some point in our careers would have come across the concept of pickles, especially if you work with Python. The concept of a pickle is very much analogous to the way for you to export your machine learning models into a way that can actually be reloaded from a file, right? And this is basically using the Python binary serialization method that allows you to basically dump your artifacts. And when it comes to actually data science, practice, pickles are much more ubiquitous than we would want, right? But we also hear that pickles have some security vulnerabilities and they can be exploited. But as practitioners, it's often something that you kind of know, but you wouldn't be able to kind of explain it exactly how pickles can be exploited, right? And what we're going to be looking at right now is exactly that: is how is your machine learning artifact going to be exploited if it can be compromised within the machine learning lifecycle. So let's actually do that. If you remember, we saved our model as a binary in a file, right, in a pickle. What we can do right now is just load that pickle, right? So using joblib.load or pickle.load, that means that we basically loaded the pickle. We see that the model that we actually exported still works as expected, right? Similar to how the scikit-learn documentation alludes to, it still works. However, what if what we now do is actually meddle with the internals of Python to ensure that whenever that pickle gets dumped, it actually dumps malicious code instead of the machine learning model as is and as you would expect. And that's actually something that we can do. In this case, Python itself uses the reduce function by default to know exactly what it should be exporting, right? In the previous example, we saw that it actually passes the module of scikit-learn, the class of logistic regression, and the parameters to initialize the model. But here we want to create a function that does something slightly different. It actually returns the OS system command that runs any arbitrary commands, and we're going to pass a string that is not easy to interpret. This is a base64 string that actually has this, basically copying all of the environment variables into a pond.txt file. But we can run any command. We can actually get all of the Kubernetes secrets and send them in an email, or we can actually like post them into a website. We can do absolutely everything, right? This runs any Linux command. So what we're going to be doing is we're going to be like, saving this function, and we're going to override our models reduce class with that function that we just created. So whenever we actually dump that function, that pickle itself, and we have a look, the pickle itself looks very different to what we were seeing before, right? Before we actually had the module, the class, and then the inputs. Over here, if we look at what's inside of that binary, we can see that there is a POSIX system, like from the POSIX module, the system, function in this case, and then this end into pon.txt, right? So we can see that already, like our pickle is a little bit dodgy, right? But the problem is that if we actually copy this pickle again into a remote bucket, similar to the steps that we carried out to deploy our model previously, and we again deploy our model, right? In this case, we're deploying it with this other bucket, which we have uploaded into the /unsafe. So we actually have like two, artifacts in our object store. When we actually look at the model, it's running correctly. But when we look inside of the actual running service, and we actually run a head on pon.txt, we can see that the actual pon.txt file got created, right? So that's actually pretty bad. The fact that we deployed what we thought was our model, and we ended up loading and running arbitrary code that we didn't expect. Let's actually try that locally. What if we actually load our unsafe model locally? We don't have any pon.txt file, right? Clearly, like, there's no pon.txt file. We load our artifact, and when we actually check, oh, there's a pon.txt file, right? So we can already see, you already have an intuition now of how these things can be exploited and why it is actually, not suboptimal to use, just artifacts without, that consideration in mind. And the interesting thing is that, pickles are ubiquitous when it comes to the machine learning ecosystem, right? Major machine learning libraries like scikit-learn or PyTorch or other libraries actually use it within its internal utilities. So the question is, well, what is the best practice whenever you're actually dealing with pickles? Of course, where possible, if you can export to other formats like Onyx, which is basically more standardized, serialization formats, then all power to that, especially given that that's going to give better performance, more optimizations. But at the same time, whenever you're loading, binaries in the case of these frameworks, there could be some questions of whether introducing advanced tools to scan the pickles for malicious objects is the way to go. But the reality is that that's not the standard. Whenever it comes to actually loading arbitrary code, be it from a repo or a Docker image or whatever resource, the current best practice is always to trust or discard, right? If you cannot trust the source where you're loading arbitrary resources that will be executed, it's important to make sure that resource can be trusted, and also the pipeline that generates those resources can be trusted, because it could be your pickle, but it could also be your CI pipeline that generates and compiles the images. If that gets compromised, then the entire workflow will be compromised. So it is less of introducing very advanced tooling that just performs malicious code scans, but instead is focusing on making sure that sort of like processes and steps and touch points can have a trust or discard type mechanism. Your ETL pipelines, your CI pipelines, etc. So let's move into the next part. So we talked about the artifact in the context of exporting it. What about the model itself? And let's actually talk about access to the model. And first of all, let's talk about black box model access. That means access to be able to consume the model as a black box to perform inference against the model without having access to the internals of the model. We have actually seen some really interesting research areas that explore how models can be exploited. In this case, a very interesting example encompasses the adversarial detection use cases. And in this case, is basically the generation of an adversarial example. An adversarial example can be something that is very intuitive when seen side by side. It's basically a technique that allows to add statistical noise to an input that makes the machine learning model predict a different input, whilst also fooling potentially a human that is looking at that input. So in this case, what would be expected to be predicted as a horse, this image of a horse, with that statistical noise added, is predicted as a dog, this truck as an automobile, and this dog as a horse, right? So you can see that it is very much something that from the naked eye you cannot see, but ultimately it is enough to actually trick the model itself. So fortunately, we actually do have some interesting resources. One of our open source libraries called Alibi Detect contains state-of-the-art algorithms for outlier detection, drift detection, and adversarial detection. So that latter point on adversarial detection is the one that I want to cover today. There are some really interesting methods that allow us to be able to leverage some of these adversarial detection components and resources to be able to introduce a component that allows you to live next to your model so that you predict whether a input may be an adversarial example or not. So in this case, you're able to actually train this autoencoder with the same inputs of the model, and then use kind of that prediction of both areas to be able to predict whether an input is a adversarial example or not. Now, this is actually a very interesting use case, and I would recommend you to try it out. This allows you to actually generate some slide attacks that give you some intuition of how you can trick your models. But ultimately, it's important to understand that when it comes to the best practices of adversarial detection, it's not just always about introducing some state-of-the-art component that will allow you to detect all of the adversarial examples themselves. It's also about the question on, that was phrased initially about access to the model itself. And when it comes to access to the model, that brings questions of role-based access control, authentication, authorization, who should be accessed to what models, with what permissions, with what groups, with what roles, etc., etc. So there are multiple ways in which this challenge could be addressed, which may not be just specifically by providing adversarial detectors with every single model deployed. And it's similar with other considerations. I will link another resource from other talks that I have given in the past around machine learning monitoring, which talks about things like explainability. When it comes to explainability, there's also a question of not just being able to explain predictions, but the question of who should have access to those explanations, right? There are questions that go deeper into the process as opposed to the machine learning itself. Now, there's also the question of not only black box model access, right, the ability to consume the model, but white box model access, the ability to access the artifact itself. And when you have white box access to the model, there are other security challenges that can arise. One of them, which actually is pointed out by this interesting piece of research, is that it has been proven to be possible extracting training data from large language models. And that could have privacy implications where personally identifiable data, where relevant, could be leaked. Similarly, for other use cases where simpler models may also require to have the whole training data next to them to be able to perform inference. So these are real challenges that have to be considered, especially when the models are being deployed in contexts where the scale is significantly larger. So that was specifically on access to the model. Now let's move to the next part, which is actually the code itself and the considerations when it comes to the machine learning runtime and the code that it would use. So we have to remember that as data science practitioners, as machine learning practitioners ourselves, we also write code, right? Even though they may be in Jupyter notebooks, it's still code. And code itself has bugs, has exploits, and has suboptimal features that may potentially cause and introduce vulnerabilities within the lifecycle. So it's important that the code that we write as machine learning practitioners goes to a certain level of ideally automated scrutiny that allows us to spot any potential risk paths within our code itself. And the great thing about this is that we can use a lot of tools like Bandit, which basically allows you to perform code scans within your Python code and highlight areas of your code that can have low, medium, and high security vulnerability issues. Now, the reason why this is important for machine learning practitioners is because there has been contexts where exploits have been introduced in machine learning libraries themselves, and specific code paths may introduce those vulnerabilities. So, you may remember some of the people in the audience that there was recently, or relatively recently, about 1 or 2 years ago, an exploit with YAML, especially the load unsafe from YAML that could be exploited. That was actually a known issue that was introduced across a large number of libraries, given that so many libraries were using this library package. Sorry, this YAML package. So this is why it's important, and for us as machine learning practitioners, to also be conscious that just because our code is related to machine learning models, it may not be under the same level of scrutiny. Given that we are now starting to put our models in production, it does have a higher level of impact. So that was kind of on the code scan side, just leveraging some of the open source tools as well as closed source tools, and then the reminder that Jupyter notebooks, when they get to certain scale, when they start getting deployed into production, or well, hopefully not, but when people start depending on those notebooks specifically for particular reasons, they themselves become code or require the same level of scrutiny as code itself. Okay, so that was specifically on code. Now let's move into dependencies. The challenge with dependencies is one that we have seen recently quite often, actually. If anyone has maintained a Python library for more than a couple of months, you may have had the situation where one day everything works, you go home, and then you come back next morning, and suddenly something is broken. And when you look at why it's broken, when nothing changed, you actually realize that the 4th, 5th level dependency didn't pin some 6th level dependency in Python, and that got upgraded, so the whole chain upwards broke, right? So the challenge with Python is that you can pin all of your 1st level dependencies, but whenever you actually do your pip install, if the 2nd level, 3rd level, 4th level dependency doesn't pin all the dependencies, you're going to end up with potential risks of those dependencies being upgraded and breaking. So of course there are challenges of stuff breaking, but there are even worse challenges when we see situations and actual cases where malicious code has been introduced to Python dependencies that have been used across a large number of other frameworks. And that actually has been, very, very high-profile announcements during the last couple of weeks. We have actually seen several Python packages that have been compromised one way or another, which is very scary, right? So introducing best practices that allow you to avoid these issues within your machine learning stack is important, especially as machine learning engineers who build this, ML servers or this infrastructure that allows you to productionize those components. And again, just emphasizing that this is not just, a fairy tale or doomsday story. This is actually something relatively common, or not relatively common, but that actually does happen. And introducing best practices does allow you to avoid some of those issues. And we've actually done some really interesting collaborations with different projects. So our machine learning serving project called ML Server has an integration with ML Flow that allows you to avoid that dynamic installation of packages. So if you've used ML Flow in the past, you know that whenever you run the artifacts, it actually all gets installed dynamically. Well, no longer that is the case. Now, whenever you actually use ML Flow with the ML Server runtime, now it actually allows you to actually have everything packaged up into a single component. So we can actually have a look at some of the ways in which we can address these challenges. We can use things like pip depth tree to see what are the relationships between our dependencies. An old school approach of addressing this is actually taking your entire pip environment and then actually storing it in a requirements.freeze file. But that is an absolutely huge file, right? Like that ends up being insanely big. A better practice is to use tools like Poetry, which actually is a tool that allows you to actually manage your dependency, that generates a poetry.log file. So whenever you run poetry install, what you have at the end is a file that contains all of your dependencies, right? Like second level, third level, fourth level dependencies that allow you to actually make sure all of those things are scanned. You can also use tools like safety, right? This safety component allows you to perform scans across all of your libraries, and it basically tells you what are the packages that actually have some issues. And I'm running in my base environment, so you can see like it's complaining about the versions and what are the versions that it actually fixes. So that's how you can address some of the vulnerabilities themselves. And you can use packages like piprot, which basically tell you which packages are too old and you should be really upgrading them. So those are some of the tools that you can use for your dependency scans. Now, finally, for the images, so one thing to remember is that whenever we actually build an image, which in this case we did, right, when we deployed our model, you didn't see the stuff that is happening underneath, but we deployed to Kubernetes that uses a image that is underneath. Those images themselves, although they bring a lot of benefits of reproducibility, they themselves can have vulnerabilities. And you can use tools like Trivy that basically perform security scans and tell you whether you have any critical vulnerabilities, et cetera, et cetera. So that's basically it. We've talked about some of the top vulnerabilities, but there are some honorable mentions that include things that are more specific on the infrastructure. Of course, given that this is a data science conference and not a Kubernetes conference, we're not going to be diving into the internals of best practices around infrastructure, right? Because otherwise, some people are going to get bored to death. But instead, I'm just going to give a few heads up of things that you have heard before, making sure that you have encryption for data or artifacts at rest and in transit, having authentication authorization within the machine learning services, and then having some of the infrastructure hardening considerations for best practice. So now we actually take a step back. If you remember, we talk about this OWASP top 10 vulnerabilities, right? We mentioned about how this industry standard has been providing a framework for those top 10 vulnerabilities. Well, now that we've actually covered the machine learning, flaws, we now have a one-to-one mapping between that OWASP top 10 and what we can call our OMLSP top 10, right? Our Open Machine Learning Security Project top 10. So similar to how we had like broken access control, this is access to black box model access. Cryptographic failures is white box model access, injection, artifact exploits, etc., etc., etc. But one of the things that I did want to do as part of this session is I didn't want this session to just be a doomsday session where I tell you how a lot of these things can be done wrongly and there is a lot of unknowns and no way to fix them. Instead, what I wanted to provide is actually some solutions and some best practices. And more importantly, a platform where I want to provide a call to action to continue this discussion to define the best practices around machine learning security. And that is through a code repository called, in this case, SecureML, right? So SML-security, similar to how the other one was FML-security. This is another repository that contains not the Flawed machine learning, but some best practices of machine learning. And more specifically, it actually contains a project-based template that gives a machine learning engineer the base tools required to actually create those productionizable, scalable capabilities with all of the security tools that we've discussed. So you can find it in that repo that I suggested. And the way that you can access it is by basically running that template that I provided. So with cookie cutter, which is like a template generation component in Python, once you actually run it against that repo, it's going to ask you a couple of questions. It's going to ask you, hey, what is going to be the name of your machine learning project? In this case, let's actually call it ODSC, server, right? Let's call it that. What is my GitHub username? So that's Alejandro Saucedo. So repo name, so it's suggesting ODSC_server. Class name, ODSC server. And in short description, a server for showcase in ODSC. And then what license? Let's go for an MIT license. So now we actually have our server there. So if we actually have a look at the folder that it generated, we can actually see there are a couple of files that are created. We have a couple of unit tests, a runtime, machine learning runtime that is created, as well as a couple of make files. If we look at the make files, what it gives us is all of the things that we discussed in regards to the solutions and best practices, right? It gives you the tools to actually generate your content environment, the tools to be able to create those reproducible poetry installs so that you have all of your artifacts saved to the multiple level dependencies. And it also gives you all of the security scan tooling, right? It gives you the commands that you can run to perform a scan of all dependencies, of the securities of all of your second, third level dependencies. It allows you to perform code scans as well as perform scans on the image that is generated, as well as the commands to generate the image, deploy your model, etc., etc. And finally, it gives you kind of like a base Python server that allows you to actually create your custom logic, which in this case, basically anything that you put inside of this predict function, basically it allows you to put your machine learning code over there. And in the init function, this is where you actually can load your artifact. This basically is a very simple example of how you can actually load a simple artifact, which in this case is just like a Lambda. It's called a Lambda server, so it just runs like a Python Lambda to just showcase some very simple way. But here you can have like loading from Onyx or loading from I don't know, like GDM, etc., etc. So this is what we wanted to do, is make sure that we continue the discussion. So please do check out these two repos, ethicalml/FML as well as SML security for both of these resources. So now with that, today we covered the anatomy of production machine learning systems. So basically how data scientists take training data to produce artifacts, how they actually create this CI pipelines to be able to deploy those models into real-time or batch models, as well as advanced monitoring components, and then all of the security considerations at each of the stages of the machine learning lifecycle. We also provided some high-level insight into the different personas that are involved. So the data scientist creating those artifacts, the machine learning engineer creating those runtime components, and the DevOps engineers that actually are responsible for managing the entire stack, right? As your machine learning capabilities grow, also does your infrastructure and the complexity of the stack itself. If you're interested in more resources, we did kind of power through a large number of components that fortunately have 1 hour deep dives that you can cover. So we have talks on CI/CD for production machine learning at scale, on monitoring for ML, on accelerating ML inference, the state of machine learning operations, as well as a lot of the tools that are used in the machine learning ecosystem. So, brief reminder to check out the repo at ethicalml/FML security. If you find any suggestions or you have any ideas, please do make sure to open it. And now we'll have some time for questions. So please do feel free to use the questions component within the webinar. So I'll pause there whilst you're able to provide some questions. So with that, thank you everybody for joining the session. I hope you enjoyed this deep dive on flawed machine learning, where we covered the top vulnerabilities in the ML life cycle, as well as how to avoid them. Thank you everybody very much. So I'll pause there for questions to be added. Well, thank you very much. Have a good day. Enjoy the conference.